Hi guys, today we're going to talk about kinematics and graphing relationships. So first, let's start up with a little exercise. Go ahead and take these shapes, divide them up into right triangles and into rectangles, and tell me what formula you would use to calculate the area of each. And pause this video now. Go. Okay, welcome back. Let's see what you got. You could have taken this triangle, divided it up into two right triangles. This one you could divide up into either a trapezoid and a right triangle, or maybe two right triangles and a rectangle. This one, I see a right triangle here and a rectangle, or you could have just used the whole trapezoid. So area of a triangle, as you know, is 1/2 base times height. So here is the base. This would be the height, and instead of rectangle being length times width, you only take half of that to find the area of a triangle. So with that said, the area of a rectangle was just length times width, or base times height. Now for a trapezoid, it's a little bit different. It's kind of like taking the average of its two heights and meeting in the middle and then treating it as a rectangle. So the area of a little trapezoid here is going to be 1/2 times, let's say base 1 plus base 2. So again, we're taking the average of these two sides, times the height. So we'll just call this height. This can be base 1 and this can be base 2. Okay, so now that you know how to calculate the area of each of these shapes, you're good to go through the rest of this lesson. Just remember your areas of shapes. Got it? Good. So essential question here, how are you going to find the final velocity of an object after it has accelerated? So you're on the highway, you got your foot on the gas pedal, and you're driving, and you want to know your final velocity after, say 3 seconds. We're just going to do this part mathematically. So let's say A with a line over it is your average acceleration. Now, if you're not changing your acceleration, you're not jerking around, then your average acceleration is the same as your constant acceleration. It doesn't change. And we know that acceleration is a change in velocity over a change in time. Let's rearrange this to solve for final velocity if we wanted to know what our velocity was after, say, 3 seconds of acceleration. So acceleration times time gives me a change in velocity, and change is final minus initial, so let's divide that up. And I hope you're taking notes here. You're writing this all down. Grab a snack, take your time. And I'm just going to add the initial velocity to my, where am I? Right here. To my left side to get final velocity. So take a look. This works graphically as a linear equation. If I graph velocity versus time, my slope of my line is my acceleration. Hi, Tazzers. You want to play? I got Tazzers here with her toy. Taz, you want to accelerate down the hallway? Ready, set, go. Kill it, kill it. Good girl. All right, so here's the acceleration of Tazzers or of the car. I cannot see that green dot, can you? Goodness. Anyway, we know our equation for a line is y equals mx plus b, and in this case, our slope is acceleration. So m is acceleration. I gotta change to red here, sorry. X is our time, and b is our initial velocity, and y is our final velocity. So let's put this to work. Now we're back to yellow. Let's try to find our final velocity for a couple problems here, and then I'll let you do 2 on your own. Hi Taz. A golf ball rolls up a hill towards a miniature golf hole. Assume that the direction towards the hole is positive. Now it's important to remember that velocity is a vector, and since acceleration is a change in velocity, acceleration is also a vector. I'm just going to sketch my diagram here. Here's my putt-putt golf course. And here's my golf ball, and it's going up a hill, and it starts at a speed of 2 meters per second, and it slows down at a constant rate or constant acceleration of 0.5 meters per second squared. So if it's slowing down, it's important to note that acceleration is actually acting in the opposite direction. If acceleration was in the same direction, that ball would be speeding up towards the hole. So it's not. Acceleration is going to be negative here because it's in the opposite direction of the velocity. So I'm going to denote the forward direction to be my positive direction and the backwards direction to be my negative direction. You always want to include a coordinate system in your problem so that it works out in the math. We want to know what the velocity is after 2 seconds. Well, we learned that final velocity is any initial velocity that it had plus acceleration, average acceleration. We're not going to deal with any jerky motions, so it's always going to be average acceleration in this course, times time. My initial velocity was 2 meters per second. Its acceleration is a negative 0.50 meters per second. Again, it's negative because the acceleration is in the opposite direction of the velocity, slowing down the ball. And our time is for 2 seconds. Calculate that. Let's see what you get. Did you get 1 meter per second? Good to go. Technically, with sig figs, 1.0 meters per second. All right, part B. What is a golf ball's velocity if the constant acceleration continues for 6 seconds? So we're going to see if this ball continues upward or if it rolls back down the hill. So all we're going to do is change the time to 6 seconds instead of 2 seconds. It still started at 2 meters per second. It has the same acceleration, negative 0.50 meters per second squared, and this time it's going for 6 seconds. And that's still equal to my final velocity over here. So plug that into your calculator, see what you get. Did you get negative 1 meter per second? If you did, you're right on. What does that tell us about the direction, though? Take a look. In the first part, the ball was, after 2 seconds, traveling at 1 meter per second. So about half of what it initially started with. So somewhere about here. But after 6 seconds, our velocity changed for the negative direction. That means it had to turn around and start speeding up in the opposite direction. Around and start speeding up in the opposite direction. Now the cool thing about this is the velocity is the same in magnitude on opposite sides of the trip. That means if the velocity was +1 here going up the hill, that means at the same position going down the hill, it should be at -1 meter per second. Lastly, describe the motion of the golf ball in words with a motion diagram. We kind of did that. Go ahead and put it in your own words. Let's try number 2. A bus is traveling at 30 kilometers per hour, speeds up at a constant rate of 3.5 meters per second squared. What velocity does it have? 6.8 seconds later. Take a look here. We have a unit in kilometers per hour, and we have a unit in meters per second squared. Kind of a problem. So if you're saying, yeah, we have to convert, you are correct. Let's go ahead and convert 30 kilometers per hour times, I need to put this in like meters per second because everything else is in SI units of meters and seconds, etc. So you're going to multiply this times 1 hour is 60 minutes times 1 minute is 60 seconds, minutes, minutes, hours, hours. My kilometers have got to go. So times 1 kilometer is 1,000 or 10 to the 3rd meters. Crunch those numbers, you should get 30,000 meters per hour, and what does that put us at? I don't even think I did that on paper. 8.33 meters per second. Somewhere in there. Question mark. So anyway, we're going to find our final velocity of our bus, and it doesn't ask us to draw. So final velocity equals initial velocity. We can go ahead and crunch numbers here. Plus acceleration times any amount of time. That's your formula. Always write your formula first. My initial velocity was 8.33 meters per second plus 3.5 meters per second squared. Since it's speeding up, we know that the velocity and the acceleration are in the same direction. We're saying it's positive. So the acceleration is making the velocity go faster or increase in magnitude. And our time was 6.8 seconds. So we get 32.13 meters per second. Bing. All right, go ahead and try number 20 on your own. Pause this video and come back when you're done. Go. All right, welcome back. For 20, you should have gotten 5.1 seconds. If you didn't, ask a friend or ask me tomorrow. 21, 9 seconds. If you got that right, don't you feel smart? Okay, let's go on to the next part. We're going to include some graphing, and we're going to find the final displacement for the object after it's done accelerating. In topic 2, we had learned that velocity is a change in displacement over a change in time. So again, we can rearrange this formula to say that constant velocity times a change in time is going to give us any displacement. The cool thing about this is area of a rectangle equals base times height. So that means that the area underneath our velocity time graph is actually going to equal displacement. So Tazers, can you run in a constant velocity for me? Ready? Go. Good job. So let's say she's running at 5 meters per second for 2 seconds, and I want to know how far she went between seconds 1 and 2. Well, mental math says, okay, this is a change of 1 second. And I'm going to multiply that by my height, which is 5 meters per second. So my answer here should be 5 meters. Ding, ding, ding. Simple, done. Velocity, 5 meters per second. Change in time was 1 second. That's 2 minus 1. Simple enough? Let's change it up a bit. Now she's going to accelerate. All right, Taz, don't fall down the stairs. So she accelerates from rest. Oops, let's go back one. She accelerates from rest at, we know is 0 meters per second. This is my velocity. Again, this is my time. And she reaches a speed of 4 meters per second. And it takes her 5 seconds. Now you're probably thinking, okay, I have a triangle here. I can go ahead and shade this in. Can y'all see that yellow? If I were to find the area of my triangle, the area of my triangle equals 1/2 base times height. Well, let's make this equation fit our formula. So what we're looking here for is a change in displacement, which is going to equal 1/2 my velocity times my time. And since our velocity is changing here, this is a delta V, change in velocity. And since our time is starting at 0 and ending at 5, we can say this is like our final time instead of change in time. And bam, we have a formula. So 1/2 our change in velocity, which was 4 minus 0, gives me 4 meters per second, times my change in time here, which is 5 seconds. Seconds will cancel. I'll be left with meters. So 1/2 of 4 is 2 times 5 gives me 10. And that is that. Constant velocity and then acceleration. So let's say Tazer's here. You're going to run for 2 seconds at constant speed, and then you're going to slow down to a stop because you're going to hit the wood floor and you're going to slide to a stop, and it's going to take you 2 seconds to stop. Ready, set, go. And she's back. I want to know what her total displacement was over this time. So I have a rectangle. I know a rectangle, the area is base times height. So I have 2 times 2 would be 4. Let's change colors a bit. So this area here, doing mental math, is 4 meters. And this area here is 1/2 of 2. Doing mental math is 4 meters. And this area here is 1/2 of 2 times 2, because this is 2 and this is 2, and 1/2 of 2 times 2 should be 2. So my total displacement should be 6 meters. Okay, let's put that into a formula. The area of a triangle is 1/2 base times height, and here I have a change in velocity from 2 meters per second down to 0 meters per second. And I have a change in time from 4 seconds, or 4 minus 2 gives me 2 seconds. Another way you could do this is to look at this as a trapezoid. And for a trapezoid, we can combine these two, because basically we're adding these two shapes together, and we can get the formula of final displacement equals initial velocity times your change in time plus 1/2 change in velocity times change in time. That gets kind of lengthy to add all these segments together. So instead we can kind of rearrange to say that our change in displacement equals 1/2 our, what we have here is a time. I want to do this, I want to do time. So 1/2 times time 1 plus time 2. We're going to take like an average of these two times the velocity, which is the height. All right, and either way you should get 6. This one's also a trapezoid, but it's sideways compared to this one. And for this one, let's say our initial velocity is 12 meters per second. Last one, I promise. And our time goes from 0 to 10 seconds. Meters per second. And my final velocity is 24 meters per second. So we know that a rectangle has an area of base times height. Well, in this case, we're going to have our initial velocity, which is 12, times our final time here, which is 10. So for the rectangle, we have our change in displacement equals initial velocity times our change in time. To find the total displacement, though, for the object as it's accelerating, we also have to add the portion in which it was accelerating. So the top part is a triangle. So for the triangle, we're going to add this displacement, 1/2 change in velocity. Okay, so this would be the change in velocity, or 24, which is our final, minus 12, which is our initial, times our change in time. Okay, so our total displacement when we add these together is going to be 1/2 change in velocity times change in time plus initial velocity times change in time. Now there's an easier way to do this. We can extract out our change in time. We can rearrange this formula to simplify it. Because if we know that acceleration, average acceleration, say change in velocity over a change in time, then Change in time times acceleration equals change in velocity. We can plug in acceleration and time here. And what we get is one of our favorite kinematics formulas. This is our distance function or displacement function. And it goes something like this. Your change in displacement equals, I'm going to do this part first, initial velocity times time plus 1/2 acceleration times time squared. Because here you have acceleration, and t times t is time squared. So if you just wanted to find the final displacement after acceleration occurred, by the way, this is d final minus d initial because it's a change, so I'm just going to add this to my other side of my formula. And I start with an initial displacement plus initial velocity times time plus 1/2 at squared. All right, so all of this was just to show you how to derive the distance function. And granted you can calculate the area underneath the velocity time graph, you will know the final displacement of the object after it has accelerated.